Lab 3, Black Hole. The main purpose is to apply Newton's laws of motion to a real application. The experiment today involves finding the mass of a black hole with the data collected from the star orbiting around it. We'll be using Newton's law of gravitation and also Newton's law of parallel and perpendicular momentum. We first have to make a few assumptions before creating our computational model. For one, the system is a star and the surroundings are the black hole. We know that the net force on the star is due solely to the black hole located at the origin. We also assume that the black hole is not moving, that the time step is 1 day, which is equal to 86,400 seconds. Then we also assume that the star has a mass of 2 times 10 to the 30 kilograms. We first initialize our g, which is a gravitational constant, which is 6.7 times 10 to the negative 11. We initialize the mass of our star and our delta t, which are from the assumptions defined before. Then we are able to create this while loop, which will iterate over the data values, initialize the velocity initial and the velocity final. Then we're able to calculate the initial and final momentums with the momentum equation, where momentum is equal to mass times velocity, which we do right here. Then we calculate the change of velocity and change of momentum, taking the final minus initial of each of those components. Then we're able to calculate the rate of change of momentum by taking the change of momentum over the change of time. Then to calculate the net force, we use Newton's second law, or the momentum principle, which states that net force is equal to rate of change of momentum, which we set right here. F net is equal to dp dt. Then we know that the net force in the parallel component is actually equal to the rate of change of the magnitude of the momentum over the change of time times the p-hat vector. The p-hat is essentially a unit vector, which we do right here. Plug in those values, are able to calculate the rate of change of momentum in the parallel direction. And using the momentum principle, we know that the parallel component of the net force is equal to the rate of change of momentum of the parallel component. Then to calculate the rate of change of momentum of the perpendicular component, we use the idea that net force is equal to the parallel component of the net force plus the perpendicular component. We're able to solve for the perpendicular component. Then we're able to set right here that the perpendicular component of the net force is equal to the rate of change of momentum of the perpendicular component. Then to calculate the mass of our star. So we take the initial Newton's law of gravitation, we're able to solve for the mass of the black hole, which is F net times r squared over the gravitational constant times the mass of the star. So to calculate the r vector for this problem, we know that the force is acting on the star. So we take the observed minus the source. So in this situation, the star would be observed as defined over here, and then the observed would be the origin, which is the black hole. Then we're able to calculate the mass of the black hole. As you can see here, we take the magnitudes of the net force and the r vector as we're dealing with magnitudes in this equation. Then we print the mass of the black hole. And as you can see in this video, the F net is defined with the orange vector. The F net parallel, which affects change in magnitude, is defined with the blue vector, and the F net perpendicular, which affects changes in direction, are defined with the pink vector. Then we can find that our mass of our black hole is 1.15 times 10 to the 34 kilograms. Our net force is 8.32 times 10 to the 28 newtons. Our F net parallel is 3.87 times 10 to the 27 newtons. And our F net perpendicular is 8.13 times 10 to the 28 newtons. Now, what does it mean? How does the net force differ from the rate of change of momentum? We know that net force causes a change in momentum. Although they're the same numerically, the net force causes an acceleration, which is a change in velocity to cause a change in momentum. As we know, momentum is equal to mass times velocity. Net force equals the rate of change in momentum, but they don't represent the same thing. Now, what if a different black hole was swapped with the original black hole? Would you be able to tell the difference if the motion remains unchanged? The answer is no. With this equation we calculated before, where the mass is equal to these components, we know that if the motion remains unchanged, everything on the right side of the equation would remain the same. Thus, the mass of the black hole would remain the same and we would not be able to tell the difference.